Hello everyone, my name is Andrew Parry. I'm a third-year PhD candidate at the University of Glasgow, and today I'm going to give you a perspective on in-context learning through the lens of IR, and more generally how we as IR practitioners can have some impact in broader NLP beyond just retrieval augmented generation. So I'll begin with some background on generative models and prompting, and I'm sure since you're in the session you're probably aware of what this is, but if you're not, by changing how a task or information is presented to a model, downstream effectiveness can frequently improve. However, models have been shown to be brittle to prompt choice, leading to the notion of prompt tuning, which some of you will definitely be familiar with. So the example shows an abstractive summarization prompt. We've begun with summarize this text, but let's say on some validation tests, we see that shorten this text was more effective. But then we try even further and we try provide a report on the core points of this text. And again, if you're familiar with prompt tuning, you might be familiar with the last one. You're a genius summarizing agent, and if you do not summarize this text, so on and so forth. This is quite a convoluted process, and one technique that's been shown to be effective in a kind of zero-shot setting is to instead provide additional demonstrations or context to provide greater gains than this prompt tuning. This is called in-context learning. So for some background on in-context learning, we are providing additional context to inference time without further updates to parameters. The example here is a decomposed prompt, so we could have a task, given a text, output a list of keywords. Our example could be IR researchers could have a lot of impact in broader NLP tasks, and there are keywords might be IR and impact. We would then have some unseen text. BM25 is a highly effective baseline that many ignore, at which point the LLM would perform the completion. So this has been shown to be a really effective and generally minimal approach in structure and tuned generative models to improve effectiveness. Examples could be completions of tasks or some other external knowledge, but should be appropriate in a given context. And we would argue that retrieval augmented generation could be seen as a clear example of such an approach. So I'm going to make the argument that RAG is in-context learning, and I think this is why you should care. So external knowledge would appear to be essential to robust performance. In-context learning usually has demonstrations, but actually could be anything. If you see the example here, we have retrieval augmented generation on the left, and we have sentiment classification with ICL on the right. In RAG, we take a query, and then we retrieve some context from a corpus in the form of text. We put this into an LLM, and that helps us to get a better answer. Whereas in sentiment classification, for example, this could be any task. We have some test instance, we have a set of examples, both go into the LLM, and this helps us to determine a class label more robustly. But we could see relevant information as just a demonstration of an answer. And I believe that naturally, therefore, IR practitioners can have an impact in this area. And obviously, we have multiple decades of research in efficiently and effectively finding information across multiple subfields. So to draw some more analogies between IR and ICL, for information retrieval, specifically an ad hoc ranking task, we retrieve a ranked list of documents given a query ordered by relevance, whereas in in-context learning, we can retrieve a ranked list of examples given a test instance. In IR, we maximize relevance of the retrieved set of documents, whereas in in-context learning, we would want to maximize the utility of a retrieved example for a downstream task. Utility could be defined depending on the downstream task. An example might be the correct information for an open QA task, or it might be a set of annotated instances that lead to a correct classification for, say, a sentiment classification task. Finally, we consider the probability ranking principle, in which a relevant document should be preferred or more probable than a non-relevant one, or in in-context learning, an example with higher utility should be retrieved at a better rank than one estimated to be less useful. So, the format of our perspective is three main verticals inspired by IR subfields. I'll go through each of them now. So we first consider that depending on an instance, we may need to adapt the number of examples or the type of examples that we have, and we frame this under query performance prediction. Our second is inspired by re-ranking, so in a cascading ranking pipeline, we're providing a smaller precision-orientated subset, and we believe this could also be beneficial in ICL. Our third is diversity to ensure task coverage, which is inspired by faceted IR. We believe that each of these verticals could be used to improve various downstream tasks as noted below. So, to begin with the first, we frame adaptive ICL under the notion of query performance prediction, which is heuristics to estimate retrieval effectiveness without ground truth. There's obviously a large literature in both supervised and unsupervised QPP, as well as pre and post retrieval. So we have a number of ways that we could apply this. You'll see some recent works, particularly at SIGIR this year, that we can use QPP for ranked list truncation. The example here shows that given a query, we would put that through a model which would return some ranked list. Let's say the colored documents are relevant. An ideal QPP estimator could truncate this list because we don't actually need to show a user that last document. In ICL, this paradigm could allow us to do a few things. We could minimize the number of examples we present while maximizing utility, given the expense of generative models in production. Also, we could provide a greater number of examples when an instance is difficult, or less examples when an instance is trivial. To give an example, we have a test instance, too slow for a science fiction, in a sentiment classification task. We go through an example retriever, which has an index of annotated examples, and then we take 2 examples. Now, you'll see in the first case, when we only provide 1 example, we end up with an incorrect classification. Whereas in the second case, when we provide 2 examples agnostic of the labels of said examples, this leads to a correct classification. Further beyond this, we draw some parallels with the k-nearest neighbors algorithm. So using the k-nearest neighbor algorithm, a non-parametric classification algorithm can be formed. The way that we do this is by observing the neighboring instances within some vector space of a test instance and aggregating their annotated ground truth to estimate the test instance posterior. These neighbors could be annotated or non-annotated examples, or just some unlabeled context from an external collection. But we consider that given the problems that can occur with KNN, and that the homogeneity of a neighborhood can be a problem, i.e. we might have all positive examples of a neighborhood, or we might have half and half, in which case it would be more difficult to robustly classify. Usually this is conditioned on the neighborhood as opposed to the input, but we consider for ICL that we can condition neighborhood size on a given input. So what we did was we trained a model to predict the neighborhood size given some instance. For an annotated training set and some values of k, where k is the number of examples, we performed in-context learning for all values of k, i.e. giving it 0 to 5 examples. In the cases where the outputs were correct, we would take the value of k that maximized confidence. We then used this optimal k to train a pre-trained language model end-to-end to predict the neighborhood size given a test instance. We performed experiments on a few different large language models and across a few different data sets, and I'll give you some evidence from the Stanford Sentiment Tree Bank. So we see initially that even just adding one few-shot example was sufficient to lead to quite a large gain in metric performance, further increasing when we increase that to 5 examples. However, when you look at our adaptive K, we're only marginally changing the number of examples, actually reducing it, and we are then, again, further improving metric performance. But what I think is even more interesting is that the Oracle K, which is where we take the minimum number of examples that led to a correct output, we only actually needed 1.22 examples on average, and it led to even further effectiveness. So applying QPP-style learning could actually lead to gains both in effectiveness and efficiency. So with respect to adaptive ICL, we pose the following open research questions. Can query variants generated by LLMs improve the prediction of the number of examples used for each instance? Can relevance feedback-based approaches, with or without the use of query variants, help reorder the initial top K towards a better prediction of K? And thirdly, can other ICL parameters also be chosen in a data-driven manner with respect to a given test instance? Our second vertical is inspired by re-ranking. So we consider that we could create supervised models for re-ranking examples where we're learning the utility of XZ pairs, where X is an example, and X is an instance and Z is an example. Obviously, as you're all aware, there's a large amount of literature in learned retrieval models, but we consider that it would be interesting to see what models are actually effective when we're moving away from topicality to some other downstream notion of utility. What I think is particularly interesting is that in this case, we have a query which goes through some retrieval pipeline and returns a ranked list. Now, Cranfield stops here, but in the case of either RAG or ICL, we then have an LLM which explicitly uses this ranked list, which allows us to get another indicator of how well we're retrieving documents. But I believe that there's some other considerations for learning to rank in ICL. We've made the analogy that X is a query and Z is documents. But does relevance actually equal utility? What happens when we combine examples? So you see in this case, we have 2 one-shot instances. One is useful, one is not useful. But what actually happens in combination is completely unknown. Do two positive examples still lead to a good outcome if they're combined? Furthermore, what about the ordering of the examples? In IR, we don't actually care if we retrieve one relevant document over another, but within ICL, we're using decoder-only models, so we actually have order sensitivity. What happens there in ICL, and can rank bias metrics still function? So with respect to our second vertical, we consider, does downstream performance correlate with the effectiveness of the retrieval system that collects examples? How faithful is the assumption that a combination of several one-shot useful examples remains useful for ICL prediction? And we also believe that there's a significant scope of improving over standard learning to rank by explicitly modeling concordance of the utility of examples, given that we have inter-example interactions. How can we adjust ranking models to account for this? Our third vertical is with respect to faceted IR, or the diversification of examples. In IR, this is looking to provide greater coverage of query facets within a ranked list. Observe the example again. So we have some query Java. This could be the coffee. This could be the programming language or the place. And we consider, how would we do this for ICL? It might require suitable adjustments. Do we want to only look at the provided context, the topicality of our examples, or do we need to look at their completions and how this affects LLM posteriors? We believe that query variants, like how query variants provide greater coverage of a topic, potentially task coverage can be improved under a similar setting. And in providing diversification, we may reduce bias induced by dependence on a corpus of examples and their completions. So with respect to our third vertical, we propose the following research questions. How sensitive is ICL towards the topical diversity of examples? Is diversity an effective feature when modeling latent dependence between an LLM decoder's input and output aligned towards a specific downstream task? How may our existing IR metrics for diversity, like alpha NDCG, be adapted to measure the effectiveness of a ranking for downstream ICL? And finally, how can multi-objective neural ranking models be trained to learn jointly downstream specific utility and diversity? In summary, we've proposed three main verticals inspired by IR to improve ICL. Additionally, we've investigated the application of QPP-style learning to example selection in ICL. And I would argue that though RAG is a natural space for IR practitioners to have an impact in broader NLP, clear parallels can be drawn between our subfields and components of modern generative systems. And I believe that IR practice and evaluation more broadly can be applied to NLP tasks as dependence on generative agents and therefore dependence on grounding from external knowledge becomes more prominent. Now, this work was done with my collaborators who unfortunately can't be here today, but Debasis Ganguly and Manish Chandra are organizing a TOYS special issue on QPP and its applications, and I hope that this talk has provided some food for thought. Thank you.